Okay, sorry about the delay. I have a presentation due tomorrow related to our advisory board and ABAT visit. So I'm a little behind schedule, sorry. Okay, let me finish the live table method. Live table method you can consider is the sloppy way of building the survival function, but or not for survival function, a survival table. But please put that down very carefully. There's no such things as hazard function, or we cannot mathematically come up with an expression or approximate it, because it's a quick and dirty method. And in the method, okay, we can count how many people, count the deaths or the event in the table, but we cannot figure out, sometimes there are things disappear, and they call it loss. But loss is not a real event, okay? And this is similar to the censorship, but censorship, we know one by one where they go. Loss means what? I open a box, check, whatever the fruit flies, number of flies I have, or number of worms or rat I have. But you count the units. You said, oh, in this box under the treatment, originally I have 250. Now I have 120, and then I have 10 deaths. Okay, supposed to be, either life or death, right? But suddenly you should realize that. But I have before I closed my box in the last review, I have 250. But now, combine the life and death together, there are some missing. So the missing one, the MIA one, or we can say is they're missing. Where did they go? We don't know. So we call those loss, okay? And since they lost, we know when we open it, when we close it, they're there. When we open it, they're not there. So we only can estimate they lost somewhere in between, in the middle time. So we use half as the time. And I know there are people, rather than using half, they're using a golden ratio, 618% as the ratio. And there are the approximation. I don't really think that you can justify that. So generally speaking, okay, 100 to 1, I don't count. Say this is a minute. The first two hours, we didn't start counting. Okay, we start our counting process after 120. 120, I open. There are 19 of them, and 150. I reopen it, I count one death, so 19, and then of course you can use the same approximation approach and said that, okay, so what's the ratio? The ratio will be, 18 out of 19 left, right? So this is the ratio. And then the other one will be this is kind of like the variance, and then there is this square root of the variance. So I have a window or approximation of that variance, and you can tell the ratio. We would like to see these things as stable as possible, and the number here, it's really put it? Well, we would like to see this number dropped in a constant way, but people just pay attention here. Here, totally, originally I have 18, the one die, and then this one is, I have one more die, right? So it's, this number is 17, and this is 18 over 19, 17 over 18, and then of course the last one is one die and nothing left, 0. Okay, so this is 0, and this one you can tell I have two die out of 4. So this is before I do the 2 die out of 4, I'm supposed to have 50%, right? If I only have 2 die out of 4, but I have one more missing. So here, look at the ratio. It's not just counting the deaths. I need to also count the one missing. So one missing is a die or a life. You don't know, right? At 240 to 270 during that time, I can see 2 bodies, so I know 2 out of 4 is deaths, and 1 is lost. I don't know where it goes. So all I can say is what? Approximately half death, half life, right in between. That's why I end up with 3.5. And then with this 3.5, you can tell 1 minus this 3.5, because I'm losing half of, I cannot count as 4. It's not really 4 anymore. It's 2 over 3.5, okay? I will end up 2 over 3.5. And if I say this is my death part, and 1 minus that death part, that's my survival part. Okay, so you know that this. Let me do it one more time. Go to 2 divided by 3.5. Okay. Oh shoot! Do it this way. We know this 2 number, 4.2, and so the death really is, if I have 2 deaths out of the 3.5, so my death rate is a little higher, and my survival rate, 1 is should be 0.25. But obviously, I don't consider this loss as totally death and totally life. That's how I end up with this number. And this one is 6, okay? But I also have 1 missing value. And then that's the same things. I don't consider I have 11. I don't consider I have 10.5. That's how I get this value, okay? Everybody know how I got column F, the proportional of survival now? Okay. The only things I would emphasize here is that this multiplication ratio coming down until I reach 0, okay? This is the same approach we have before, right? Upstairs times the current value, drop until I reach 0. You know that, okay, at the beginning, okay, when your survival rate is really, really high, okay, 1 of the 19, which one you pick, this is very small variation that you can pick. But at the end, you can tell that variations increase dramatically because, I really don't have too many sample I can choose from. So technically speaking, you can see this value is getting bigger and bigger because the variation level is getting bigger and bigger. And what we want is we would like to keep this value as small as possible. So in other words, if let me do something here, okay? If, every value I have here plus 40. Okay, and let me just use this value, Control C, and paste special value. Okay, you guys see here? This, I'm drop, right? But see the variation of that drop, it's very, very small. And insurance company usually, when they operate on a live table, do you think they will play with the insurance at the survival rate at almost zero, or they would like to play at least at this level? So whenever you want to do live table, you actually prefer, or you want to sell insurance, you want to make sure your survival function is at reasonably high level. So the chance of accident is very small. But then this value, you want to be as constant and as small as possible. You don't want to operate on a very, very huge value here. Because if you operate on a huge value here, this is like this, right? 4 people, you sell insurance to 4 people, and you know that half of them are gonna die. That's not a very reasonable insurance to sell. Right before the beginning of COVID, okay, when COVID just started, and there are special insurance, underwritten by several insurance companies around the world, because at the time, what was their assumption? Oh, this thing's gonna among certain population with preconditioning, so they keep selling the insurance and they're making a lot of money because the death rate increasing, but relatively speaking, they're playing at a very high survival rate. But then, once it starts spreading, they realize that they cannot control their life table shown is totally opposite. So they shut down that kind of insurance immediately. So this is not as popularly used for reliability or survival analysis, reliability analysis, but this is a life table is widely used for insurance company for approximation. Okay. Everybody get this part? Okay, now let's go to Cox regression. This is probably the most useful in survival analysis, and I hope you can stop me anytime if you cannot follow the math, okay? And to talk about this, we really need to have a odds ratio function, and the odds ratio function is this, okay? I assume the probabilities of having an event is following this formula. And what is this parameter B? Could be anything, okay? And let me show you an Excel file. And I'm going to repeat this one more time once I start talking about judgment okay. So for example, give me a B value. Say I'll let B, okay, B value equal to B. And this thing, let's just say equal to something. Right now, let's say just equal to 2. Okay? And then where is this 2 coming from? Let me give me a sec and think how I'm going to play this. Let's just, yeah, let me just let it equal to 2. And then let's start from, and then let's have a time, or x, or time. Okay? Start by negative 10. And equal to this plus 1. And I'm going to just do this. Okay? And then let's just say the parameter equal to that value. So my p value equal to, okay, 1 divided by 1 plus exponential. This value as a constant times whatever t I have. Okay, sorry, I need to have a negative sign here. Okay. Okay, so people first look at this. Insert a function. Okay? What did you see? You see this value is very, very small, almost 0, and transfer to 1. Right? So if I want to say that this could be a CDF, would you agree with me? No, this is because CDF is what? 0 to 1 monotonically increase. So is that it? And I can make this a little more, and then I said, you know what? I don't like this start from negative 10. So I will just say that plus 10 as a constant. Why am I going to move them plus 10? Because I want them to get out of the negative region. So now this is a transfer function from 0 to 1, from 0 to x from time from 0 to 10, and this from here to here. And then here, let me play one more game. This is called logistic regression or logistic function, because it's a, and some people use arctangent for this, but we just use this. Okay, what if I use 3? Okay, that'll, move even faster from 0. And then if I don't want to use 3, I just use 0.5. Oh, that's too slow. Let's just say I use 1.3. Okay, and you can tell if I copy this, Control C, Control V, this value will move that's not what I want. Redo it. Insert. Okay. So first thing first, everybody agree I have this value whatever inside that B could be a regression was 2 parameter. Beta 0 is 10 plus beta 1 is 1.3 times time. And I can change my value. I don't want to start from 10. I can start from 11. Can I do that? And then just Control C, Control V. Okay? So I can change where I start. You know, if you want a 10.5, that's fine. And I can change the value here, 1.3 to 1.35. Okay? Or 1.3, 1.5. The higher the value right now is, the steeper the slope. Okay? And if I use 0.9, it will be shallow. Okay? And let's say use 1.1 for now. Okay? Now, if this is P, means that something, you know, B0 could be, starting points of a disease at age 10, or puberty start at 10. And then certain calcium depletion or something bad or something happened with a ratio of 1.1%. And so people just start having that problem getting worse and worse. And when they reach 15, it's really, really bad. And so if that's the P, this is 1 minus P. And 1 minus P should be 1 minus this value, right? And then you can tell that value is, when P increasing, this value is decreasing. So back to the algebra. I have a disease or a parameter. This parameter, let me just use capital B here rather than small b. But what's in there could be a B0, B1x. Later on, I can have B2, X2, B3, X3. Doesn't matter. All you care about is that whatever those things I add in, that contribute to this B. And if this is the things I contribute to the B, 1 minus P become 1 minus this things, this expression in the denominator, and 1 become on the top. So this term becomes this. And so now you see the two things, 1 minus P become exponential, whatever involved over this denominator. If that's the case, so P over 1 minus P become this expression over this expression become 1 over negative exponential B, and so become exponential B. So what does that mean? P is something bad going to happen. 1 minus P is I've survived, still so far nothing happened. So we call this P over 1 over P. Something bad happened over something maybe not going to happen. Okay? This P over 1 minus P, we call it odds. Okay? And then if you have the odds is negative 1 exponential B. And if this is exponential B, whatever involved in a B could be a simple regression, B0 plus B1x, could be B2, X2, B3, X3. Who knows how many different bad things going to involve with a baseline B0 and then B1, B2, tons of stuff involved. But what we care is that then there is this thing we're going to measure. It's called odds ratio, which is log odds ratio is this term. And once you take log of this, you bring everything in the exponent down to the floor. So log odds ratio becomes a potential regression. And once it becomes potential regression, you guys know, if you, in DOE I mentioned, you can become what? Log odds ratio is y. And here is the x part. So the parameter become what? X transpose X inverse X transpose Y. So we can abuse our statistics easily, okay? So that is the reason I'm going to do that, and let me do it here. So okay. First, I will do this, and then odds become this guy over this guy. Okay? And then, of course, log odds become ln of this number. And we know that this number, because I added 11, so if I minus 11, plus 11, I minus 11 before, plus 11, plus 11. No. Plus 10, right? Hold on. Plus 11. And, oh. And if this whole thing's y equal to if I use this times this plus 11. I'm trying to recover the value back, but I can't. I don't know where I did wrong. Oh, I know that. .1. Okay, one more time. Negative. Anybody see where I get wrong? Okay, P. Let me do it with okay. I mean, try not to shift it to see if I can get it right. 0 is 0.5 is correct. 1. Odds ratio 1.6. Okay. And then log odds ratio. And okay. Okay, now I recover both sides. Log odds ratio is equal to some beta 0 plus this. Now let's add another term. Okay, let's just call this is my B1 or B2. This is my B0 and B1x. So I'll do this the same way. B equal to B0 plus B1 times time. Okay, and then now I'm going to call this as my B0. So, or B1. Oh, that's my B1. So, B0, let it be a constant. Let's say 2 or 10. Let's use 2. If it's too big, I'm going to be in trouble again. And then here's my B1. Okay, so here, this will equal to B1, and then I need a B0 term. I say this is my B0 term plus, and let that be constant too. Okay. Exponential B1 times time, and B0 is this term. Control C. It didn't allow me to be that big. I don't know why. Let me just use 0.5 for now. Exponent. B1 is the ratio. B0 is the constant. I should be correct. What happened here? Victoria, can you help me? Huh? Okay, I'm basically trying to repeat this numerically. I have exponential, negative. Here's my B term.
Is it supposed to be down here? C6?
Oh, no. That should be here. Okay.
It's locked. It's just on the. It was on the wrong cell.
Okay. So let's see. Okay. And 1 minus P, odds ratio, log odds ratio. And here I need to minus 0.5.
Did you lock A4? Or are you keeping A4?
I'm keeping A4. that's wrong.
Okay, click on the formula.
No, hold on. I'm trying to do this. Maybe I can do it the other way. If I'm using this guy minus this guy times this guy, that's 4. Okay, I got it right this time. And this is my, here. I think I got it right this time, but let's play with it a little harder. 0.8. Yeah, it's 0.8. So, okay, finally I recover my disaster here. Okay, I have a B0 and B1. I just made it up, some number. I'm trying to show you that T, and then you have your event, and 1 minus P is the survival. So 1 go from 0 to 1, 1 from 1 down to 0. And the odds ratio is this strange number. And this number will grow like crazy. So once you take the log, this number will become constant. And so now, if I'm saying that I have a baseline, where is that baseline? Let's see if I change this to 2.8. Yeah, okay. Okay, so odds ratio basically is a regression to be found. If I can calculate the odds ratio and I know B0 and B1, I can get to that. Okay, and this is called logistic regression. Okay, how many of you know how to do logistic regression by hand? Or using Excel, using X transpose X, X transpose Y inverse, you can do that, right? Yeah, okay. So, so basically what I'm saying that if, okay, for example, if I add a random number here, a tiny, tiny random number here, divided by 10, okay? And you, random number divided by 100, maybe, even divided by 40. Okay. So now it's not a perfect regression odds ratio, right? It's because I add some random number in there, but oh, it's just too much over 1. So you cannot have a number over 1 because then now you have a negative. Log negative is impossible. So let me do this. Times a random number times smaller than 1's number. Forget it. I'll make the randomization somewhere else. Let me show you how. Okay? So let's just say that the odds ratio I calculated is not a real odds ratio. It's a smaller number I add, right? So if I add my uncertainty here, please show hand. I know you know how to do regression by hand. You know. Do you know how to do regression by hand? X transpose X, X transpose Y. Basically, if I give you a set of random number, can you figure out a regression by hand? Okay. And let me just do this. You know what? Let me do the regression later. Right now, let me finish because I already waste a few minutes here. And later on, I'll show you how to recover 2.8 and 1.1 by hand using regression. But here I'm just trying to say that what is proportional hazard function? Proportional hazard function is basically said that, oh, there is a hazard function, okay? Linear regression saying y is a regression of b0, b1, bx. And logistic regression said log odds ratio is a b0, b1, bx, okay? And if you're doing queuing theory, the Poisson arrival rate could be a regression function and saying that, oh, my arrival rate log is based on, you know, I have a festival, some holidays, and my traffic will increase or decrease. So log arrival rate is this function. Now, here we're saying that it's not the odds ratio follow a regression. It's the hazard function. Remember what is the hazard function? Can anybody tell me what is a hazard function? Hazard function is a conditional probability. Is what divided by what? Is the PDF divided by what? Anybody? Survival, exactly. Why? Because we're talking about an event, right? So that's the PDF. Happen, but can you talk about, oh, how dangerous at age 40? No, you first need to condition on you survive at age 40. So hazard at 40, age 40. Age 40 equal to what? Well, let me just put it here. Age, new page. Hazard function, age 40, ht. And t is from somewhere, you know, 0 to somewhere. But I know age 40 equal to what? Equal to F40 divided by S40, right? Right? This is something you should learn based on what we learned so far, right? And now, what we really want to say is that, oh, why this? So this is what we're trying to see, right? But now we're saying that these things, F40 by S40, this function could be constant if it's exponential distribution. If it's going up, for Weibull, is increasing, hazard function increasing over time. If is so the shape parameter is greater than 1 or something, right? That this function itself, I cannot put them in a regression. However, if I put them in a log and said that it's a log ht, okay? If I say this is a log ht, this log ht can be modeled by some parameter. So you say that, oh, so-and-so, how hazard at age 40? And I'm going to ask a few questions. Does he smoke? Oh, he smoke? Then there will be a negative parameter for smoking. Does it drinks? Oh, he drink red wine, but it's 1 glass per day. Oh, then it's positive. But if he drinks, beer or hot liquor, 1 bottle a day, that's terrible. Then that could be decreasing. So there will be a bunch of X increasing, decreasing because of his personal parameter. So once you have all those personal parameters, you have them all together, you basically can say that that is his log hazard ratio. And then you can use that value to model the hazard function. And what's the beauty of this? You can, for insurance company, for biological data, you basically say that, okay, what's the nature, what's the nurture of this person? You know his nature, his nurture, his background, his income, whatever, the things you think is significant, you can later figure out that based on this, what is his log hazard? If I give you an airplane and said, oh, during COVID, we retired this airplane. We let it sit in some desert in Arizona because we don't have enough traffic. And then you want to say that, well, after 2 years or 3 years of shutdown, now the airline want to bring this airplane back. And you want to know that how old is this airplane? Is this airplane airworthy? And you basically said that, well, what's the previous conditions? Okay, how many flight hours, under what kind of maintenance mechanism, under external contractor or internal contractor. You have a bunch of X, you put that in, you will figure out his log hazard ratio and said, oh, this airplane, based on the parameter, is it good enough to bring back, or we need to do something about it, or just give it up, okay? So now we're saying log regression is, Cox regression is we're trying to model the hazard function, proportional hazard. And the beauty of this is that we're going to model the hazard function. To model that, you have to say that I have a baseline hazard, but lambda 0. And what is this lambda 0 t? I don't know, but it's a baseline. And since everybody got the same baseline hazard, and after that, I have a bunch of exponential beta x1, beta x2 to beta k xk, those things that are individual characteristic dependent. As such, when you take the log of this, it becomes log beta lambda 0 t plus all those hazard characteristics. And put it down here. The lambda 0 is the baseline hazard, means everybody got the same hazard. But the beauty of this is that once you do that, it's almost like the odds ratio is when you have two hazard functions combined, say HI is someone smoke, 1 pack a day, HJ is someone who's non-smoker, compare the two. Lambda 0 and lambda 0, the baseline cancel out each other. Whatever leftover is exponential over exponential become exponential of the beta differences. So if you use this beta differences and take the log, you can get rid of the exponential, and you can see that everything's the same except whatever you want to consider. So for example, if I have one is, 60 years old, everything's the same. So they have identical baseline hazard, but one smoking 1 pack a day, one smoking 0, and both 60 years old. So 60 over 60 cancel out. The baseline hazard cancel out. The only difference is someone smoked 1 pack a day. What is his hazard? for lung cancer. And I can do it the other way around. Look at this one. I have someone both identical baseline hazard, both non-smoker, but one is 70 years older than the other one is 60 years old. So here is the hazard ratio for 10 years differences between a non-smoker 70 over a non-smoker 60. Can you guys see that? Okay. So here comes the example. Now we can do likelihood ratio. But remember, this time we don't call it a likelihood ratio, not like our Kaplan-Meier before. This is a lot trickier. I'm going to have one example, but later we're going to do it by hand once. But well, let SAS do it. Consider this, okay? I have 6 subjects. And all 6 subjects, we're going to evaluate when something bad happened, okay? So since they have exactly the same hazard baseline, so we just basically said that, at time 1, one of the guys died. So at time 1, what is the hazard ratio? Is 1 out, but when H1 is out at time 1. But there are 6 subjects. H1 is 1, H2 is 1, H3 is 1, H4 is 1, H5 is 1. Everybody is 1. Everybody could be out, but only subject 1 is out at time 1. So the first partial hazard ratio, the partial likelihood is this value. And then at time 3, okay, 2, 3, 4, 5, 6, 2 is out. So can someone tell me what is the difference between the first hazard ratio and the second hazard ratio? Yao-Ming, your turn. Tell me what is the difference between the first one and the second one. Well, I know first one is on the top, first guy out, second guy's out, first guy out at time 1, the second guy out at time 3. Then, yeah?
So is it considering like the different alternatives without considering like the initial?
Well, we don't care who's number 1, number 2, but look at time 1, how many people in the denominator? 6. But at the second time, at time 3, how many in the denominator? 5. Why only 5? Because at the time 1, one of the 6 is out. See that? So same thing. At time 4, number 3 is out. So how many people you think should be in the denominator? Only 4, because this guy's out, this guy's out. And then, of course, here's one thing you should pay attention to. Do I have H4? I don't have H4. Why I don't have H4? Because H4 never is, at time 10, he walked away as a plus. He got censored. So I don't have H4, but I have H4. Do I have H5? I have H5. But H5, I only have 2 guys left. And then H6, I have 1 left. Okay? So this is the part that I count the likelihood of failure. You should ask me one question. Do you think we should consider the value of the censor guy? Do we? What do we know about this number 4? He walked away at time 10, right? Before he walked away, is he alive or he's dead? He's alive. So we should consider that he should be contributing to the survival part, not the hazard part. to this function. As such, okay, we can write this whole things as the following part, okay? We multiply this, and like I said, we don't really know what is inside the H1, H2. All we know is a beta line, baseline times exponential something something, right? This is the hazard part, okay? And then we just multiply this all the way to the end. And we call this likelihood function L, okay? And log L becomes this log likelihood function of this whole things, except here, okay? If beta is 0, I'm sorry, here we were putting in this, this parameter, okay? We call this parameter delta here, okay? Delta, if delta is 0, okay, means that it got censored out, and if delta equal to 1, okay, then we will continue the counting. And when this whole thing's done, and we basically try to maximize this likelihood ratio. And why we try to maximize this ratio is I know how to explain this. It's almost like this example here. Everything's we're trying to do is we're trying to estimate the parameter. And if I'm using a wrong, say I'm using a wrong beta value, if I'm using a wrong beta value to estimate this many things, okay? Every time when I plug in the beta value, okay, this ratios will be very, very small or very, very big. I'm out of the position, then the value will be small. And then if you use a small value times a small value, the log odds ratio multiplications will be wrong, and then will become smaller and smaller. So what we're trying to do here is try to say that, can I find a set of beta to make these things as big as possible? And to do that, okay, I will basically need to take the first derivative of this function equal to 0, and second function for the maximization, the second derivative of the beta should be what? Should be less than 0 in order to find the maximum, okay? Okay, let me use this example to demonstrate that. Okay, so I have, ignore the ID, just subject number 6, number 2. At month 6, okay, there's an event, and fracture, no fracture, and we start the function for the okay. So let me use this one to show. At time 6, there's an event. Okay? At time 6, there's an event. Numerical example. And how many people could be in the denominator? There are 1, 2, 3, 4, 7 subjects, right? And all 7 subjects could be in the event, okay? And we will try to estimate which one will be in the event, but here we need to count how many is in the 1. Means that actually got a event. There are 4 of them could be in an event, but 0 means that they got censor 1 out. So here is the ratio between the 2. Okay, and then at time 12, I have again I have another ratio, and 17 and 20. I just keep doing this until I have all of them done. Okay? I think I need more time to explain this next time. I'm not going to do a good job today. So, see you Thursday.
I think they usually have a restore. Why?
I want to.
Recent. You just open it.
Huh?